Thanks. Okay, now the last section I'm going to talk about is carbon farming. So let's see, the idea here with the carbon farming is like we can kind of have a through line from the previous discussions. If we can stipulate that there is, you know, a carbon market, and we can stipulate that we have the ability to connect that carbon market to farm practices, and that carbon price is sufficiently high that farmers could theoretically want to go after profiting from just leveraging their land to do carbon removal and management, we could envision a future where farmers make the choice to harvest carbon as their primary product. And so that's what we endeavor to talk about here. And how would that, like, what types of technology we need to develop, or how would we think about ag differently if we lived in such a world? Okay, so as I mentioned earlier, in the future, we're going to have a very big need for negative emissions technologies. The world of carbon dioxide removal is going to be very big. We're going to deploy not just biological approaches, not just, engineered approaches, not just, hybrid approaches. We're going to deploy all of them. But I'm going to talk about here the biological approaches, specifically, how do we leverage terrestrial lands, ag lands to do carbon removal and management. And, there are already options envisioned for the future, but, today carbon assets are overwhelmingly bio-based, right? Buyers are looking for high quality carbon removal projects right now. So, Microsoft has made a commitment, 1.3 million tons purchased. They're targeting a price of $15 per ton. And there's issues with, not just the amount of commitments that folks are going to make, but also the price that they're willing to pay. And so they're looking for high quality, low cost carbon removal projects. And there is room for all approaches, right? With many of today's carbon removal options being shorter term, like, the carbon is estimated to be removed for shorter than, say, 100 years in some of these biological systems, soil carbon systems. These short-term options complement longer-term strategies by offering near-term and large-scale removal as longer-term storage mechanisms are developed, like DAC and DOC and these sorts of things. So there's the prospect in the near term of having low-cost but scalable, large carbon removal capacities in our terrestrial lands. In fact, this is the opportunity space. Ultimately, when we look at, the size of demand for carbon removal and, the optimistic estimate for direct air capture pricing, there is significant volume of demand for solutions capable of offering carbon removal at a lower price. And some of these biological solutions or carbon farming, they're low energy, they're large scale, they're low cost solutions to carbon sequestration. And that's the opportunity space that can be pursued in developing technologies to kind of augment their capacity. Agriculture has been identified as a promising supplier, right, with a significant volume of carbon removal possible at less than $50 per ton. This was another, slide or another, table from that negative emission technologies study that I mentioned. Development of, some of the things to make this possible are development and measurement and monitoring technologies. There needs to be agricultural system field work as well as the potential to demonstrate, scaling up of this. And, one of the reasons why, the agriculture has such a potential is in part due to the loss of soil carbon due to intensive agricultural practices. Approximately 12 gigatons of carbon have been lost. So what you see in this plot are, you can see all the places where human activity is, manipulated the land, and in all of those places there's been loss of carbon. And so there's a store of where we could put more carbon back in the soil that has been lost, and it's ironically the same place that we're already managing and manipulating. And soil carbon benefits go beyond carbon dioxide removal. They offer, significant boosts to soil health and productivity. And, depending on how you design your, carbon farming types of systems, they could offer additional ecosystem services, biodiversity, water storage, and all kinds of different benefits. And so, the full value from carbon farming could go beyond just carbon markets and carbon removal. ARPA-E is playing an active role in funding the development of the technologies to enhance the role of agriculture in carbon drawdown and environmental sustainability. I talked about, what Terra and Roots, I'll talk about what Terra and Roots are doing in just a second. I talked about smart farm measuring the outcomes, and then there's a new opportunity space for, developing and implementing, dedicated systems in terrestrial lands and ag lands to do carbon removal and management. So let me talk about the Terra and Roots programs very quickly upstream. So, we like to think that our projects are developing the tools to democratize crop breeding with the potential for identifying traits that improve water and nutrient efficiency and increase root matter in soils to draw down more carbon. So the idea here, these are the data play. We needed to develop technologies to identify phenotypic characteristics of plants that can be tied to genotypic characteristics of plants so that we could more rapidly engineer crops to be, better accumulators, more efficient accumulators of biomass, so you can more rapidly grow more robust crops above ground. That was the Terra program, as well as to identify phenotypes for root systems that are deeper, more recalcitrant, or that may accumulate and secrete recalcitrant carbon compounds that increase soil carbon. That's the Roots program. So this program sought to build the tools that would allow us to effectively and quickly breed and engineer crops that are just better for the purposes of doing carbon farming. An example of one of the Terra phenotyping platforms, though Griffin Purdue didn't work with Clemson to develop the CCS Solargum Hybrid, this CCS improved hybrid has increased carbon fixation rates and improved nitrogen utilization, improving the overall carbon sequestration potential, especially visible after harvest, as shown in the bottom images. So, we're developing some of these systems that can, get information and then use that information to breed and actually come up with seeds that can be produced for these better crops. Another one, another performer from the Roots program. These are ones where we were looking at images of roots so that we could identify different, attributes of different root systems as a function of a plant's, genes. We developed kind of a low field magnetic resonance imaging that allows non-destructive imaging of roots in the field. So without having to, pull the plant out by the roots to study the roots, we're able to look at the roots with these systems. And this could be a, a real game changer for, identifying attributes and deploying new technologies in the field. And, another outcome here is ecosystem level modeling. This model enables the high resolution soil and crop data to be correlated with remote sensing and scale up insight to a landscape level that could inform management strategies and understand the GHG fluxes. This builds on the Comet Planner, the Comet Farm model to account for specific phenotypes. This figure shows different carbon fluxes in different soil layers. And lastly, I want to highlight a technology that came out of the project at Iowa State University that was led by Liang Dong, which is, being commercialized by a startup called InGenius Ag. It uses silicon-based microfabrication techniques to produce microneedles containing nitrate-specific electrodes, which will enable very low-cost production at scale. It's been demonstrated to measure both in plant nitrate levels and groundwater concentrations. Its performance is comparable to existing commercial sensors, but it can operate continuously in the field for weeks at a time. So this is a real, tool that has been developed to give real-time information about, crop nutrient and water cycling, which is a critical importance when making decisions. So that was the Terra and Roots programs, and that's what's come out of it. And now we're trying to think about, I went through what the Smart Farm program was, but now why would we think about pursuing a dedicated program to do carbon farming, to engineer ecosystems and engineer crop systems and plants to perform carbon removal and management? And why is there an opportunity space? Well, of course, we have a number of tools that make this possible and make it right now, right? So we didn't have these just a few years ago. We have advanced climate modeling and remote sensing tools that will allow us, the quantification and extrapolation of carbon farming approaches. We have robotics and digital ag tools to implement novel management plans. Some of these came out of the Terra Roots programs. We have machine learning tools for optimizing biological pathways of enhanced plants, or microbial consortia designs, and lab automation for generating the organisms efficiently. And finally, we have genome editing tools that have matured to allow the targeted biological modification of crops for these improved attributes that would be necessary in carbon farming. And so when I talk about what carbon farming is, let me highlight that we kind of view it as there's two separate approaches here. And there may be like a near-term versus long-term type of strategy, but a lot of this is going to depend on, what types of carbon prices are available, what kinds of technologies are available to measure them. That's going to depend on the success of Smart Farm. But, the first is kind of this parallel approach, right? Where you can continue growing, as a farmer, if you're a corn farmer, you continue growing corn or rice or beans or what have you. And then you implement strategies that can, drive down your above ground emissions and increase your soil carbon. So you become kind of a dual purpose farmer where you produce and get paid for the yield of your primary crop. And then you would, get paid for your carbon crop in tandem. And you would be trying to optimize both the yield of your primary crop and your carbon removal capacity in tandem. The other is an exclusive approach where, farmers would implement strategies, new types of crop systems, new kind of farming approaches to explicitly go after the value in carbon markets, and they would exclusively become, carbon farmers. And there's a lot of opportunity because of the various types of managed lands that we have in the United States and how we manage them. There's a number of different technologies that we could imagine developing and deploying into different types of agricultural systems, and not even necessarily agricultural systems, but any kind of managed land that we had. We could think about how we would use that land and what types of technologies would need to be developed to improve the capacity for our terrestrial systems to remove and manage carbon. Note here that land managers are looking to unlock revenue, new revenue streams, and this is because farms have operated in the red for a very long time, and with even like a $15 a ton price, which is about what farmers can expect to gain from today's markets, you can see the potential revenue per acre that they could achieve under different carbon removal scenarios. The real thing to note here is that getting to the top blue line here of 3.5 tons of CO2 per acre will require some innovation. Maybe 1 ton or maybe even 1.75 tons could be possible through the implementation of best practices now. but to get to 2.5 or 3.5 is going to require new innovations that go beyond the state of the art, which is, no-till and cover cropping and different types of rotations. You're going to have to really move. And so there's an opportunity to develop these new types of technologies. And, it's not entirely certain that carbon prices will rise, significantly beyond, the $15 to $30 per ton range outside of, the low carbon fuel standard, which I mentioned had, $200, per ton prices. I want to note here that what we're looking at is, the price, per ton on the left-hand side for carbon. Note that DAC is the upper line here, and that the bottom line is the price that Microsoft has said that it would be willing to pay for soil carbon offsets. These are voluntarily disclosed internal carbon prices reported and mentioned here, and the companies that are willing to pay this are also listed, and there are numerous ones. These can be like General Motors, Cargill, ConocoPhillips, all kinds of different ones. And so carbon farming can kind of fit easily within this this limit of what folks are willing to pay and offer carbon removal options for right types of prices. So what I want to dive into now is to talk about what are the strategies that can be implemented, what are the technologies that can be developed to actually fundamentally change how a plant or a crop or a farm system or a managed land system can be augmented or changed to improve, the prospects of increasing carbon management and removal. So here's a sampling of potential biological engineering strategies that can be implemented. There's really 3 high-level ones that I want to mention. So, the first strategy is you could engineer soil microbiomes or soil microbes, or the interactions between soil microbiomes and root systems to improve both carbon and nitrogen efficiency in ag systems. Another approach is you can potentially engineer the metabolism of plants to accumulate carbon and flux that carbon underground into their root systems to grow deeper roots, more recalcitrant roots, or to even accumulate and secrete carbon compounds that can accumulate in the soil to increase soil carbon. And then there are approaches that you can implement to, re-engineer the photorespiratory pathways in plants to make their fixation and utilization of carbon more efficient. And so, or maybe you could even implement a number of these different strategies in tandem to really maximize the potential. Now, there's a number of efforts that are ongoing looking at some of these, various approaches. As I was saying, one of the approaches is to, have reformulate the plant's metabolism to direct carbon into soils. There's a number of groups that are doing this from Colorado State. The Salk Institute's looking at this and, has had some, high profile coverage and has, published some work on this, as well as UC Riverside in California. And the potential for, increasing and removing carbon from, just root systems is quite large. The deployment of crops that, simply translocate more carbon below ground could potentially sequester, 0.5 gigaton of CO2 annually. These were estimates that were done, as part of our, our Terra program. And, there's a lot of, simplifying assumptions that went into this, but we believe that, when you couple the estimates that went into this with potentially, frontier technologies and new technologies that we're pursuing or thinking about or hearing about, it could be greater than that. I mentioned that the other way to engineer these systems would be to identify microbial consortia and engineer those consortia to have different interactions with root systems, or to change the the ecosystem dynamics of a soil system to improve the productivity of plants, their ability to fix nitrogen or to accumulate deeper or more recalcitrant roots. And I wanted to highlight, one of these enabling types of technologies that we've recently learned about. And this is from Concerto. And I saw that the CEO of this company was in one of the breakouts earlier. But, we really think this is a really interesting thing. This is one of these enabling technologies that's just become, available in the past few years, where we can really begin to, believe that we can engineer, not just an individual microorganism, but we can get information about the interactions between multiple microorganisms to understand how they interact dynamically and how their interactions confer larger ecosystem outputs, such that you could engineer unique types of ecosystems, maybe even thinking about, we talk about synthetic biology, imagine synthetic ecology that is enabled through the tools that are coming out of some of our biotech companies. And this is something that can be applied to, complex environmental systems to engineer better ecosystems that are more capable of removing and managing carbon. Another thing that we can think about in this carbon farming space, beyond how we would engineer plants or soils or root systems, is to think about how we might be able to engineer hybrid biological geochemical solutions that would confer some longer term storage prospects into our terrestrial systems, which has traditionally been viewed as something of a challenge, kind of broadly, to accessing the most valuable carbon markets in the system, that the permanence issue. So, geochemical and hybrid biological geochemical solutions, they're a game changer in terms of timescales, with carbon sequestration timescales on the order of thousands or to tens of thousands of years at least, and up to 1 million years with carbonate formation from silicate weathering. 3 potential geochemical and hybrid biological chemical solutions for carbon storage on terrestrial land are, biochar for soil carbon storage, application of crushed silicates to farmland for enhanced weathering, and advanced plants to speed weathering and produce long-lived carbon-containing minerals called phytoliths. So I'm going to quickly go through a couple of these. I have to call out one of my colleagues from ARPA-E has developed, these slides, a fellow, and so I'm not the expert in these specific hybrid approaches, but I will try to answer questions if there are on these later. Now, biochar is, charcoal for, it's charcoal that is formed, from pyrolysis of biomass. And so I had mentioned earlier that this is one of these hybrid approaches where, you accumulate the carbon in biomass and then you match up with a downstream system. Through this pyrolysis process, you make and store the carbon in a recalcitrant form in biomass. And biochar can be formed from essentially any biomass, including waste. One of the major uses of biochar is application to soil as a fertilizer. It's effective as a source of nutrients, and it lowers the rates of nutrient runoff. And it acts as a structure on which microbes can grow, which keeps soil productive and healthy. And, there's just a lot of, utility for this biochar. I've even seen a lot of, research coming out lately where they put the biochar into anaerobic digesters, and it confers, benefits in the production of biogas in those systems. So there's a lot of unique synergies for biochar to be fed into traditional carbon cycling, circular economy types of scenarios for carbon management. So it's a good one. There's a number of folks that are looking at, the implications of biochar, both from a research aspect, and then also connecting, these things to, how they can be scaled and comparing their value compared to other types of carbon removal strategies. Crushed silicates for carbon mineralization. This is the opportunity of, kind of allowing, non-organic or inorganic chemistry that allows for carbon removal and storage to be distributed over, terrestrial lands, and then to have these, silicates remove and store carbon, but then also confer benefits in soils. The other thing to point out here is that these reactions proceed to very stable products where the carbon that is stored will be stored for long periods of time in these terrestrial systems, much longer than the organic carbon that can be accumulated through traditional biological approaches. And there are a couple different teams looking at the implications for thinking about using crushed silicates for carbon mineralization and coupling that with applications in ag systems. And then a final, kind of area that I wanted to talk about is the ability to kind of co-engineer inorganic, carbon weathering chemistry with engineered biological systems, whereby the interactions between the inorganic reactions can be facilitated or augmented by the biological systems or root systems or plant systems that are with them. And this could be even through, soil microbe interactions as well. So there's a lot of different ways you would think differently about how you would engineer crops and engineer land management practices if the goal was to maximize carbon removal is the high level point that I wanted to make. And so there are, again, highlighting here the teams that are thinking about this, are doing research in this space, and that we have to give them credit for that. So I want to, kind of recap about what we talked about today, about carbon farming. We talked about the significant potential for agriculture to play a role in carbon drawdown, that new tech developments have paved the way for innovative carbon farming systems that are low cost, low energy, large scale. That's what really makes these types of carbon removal systems advantageous in the near term compared to the engineered approaches that can be scaled in different ways and in lands that are less productive. But this is not a solved problem, and there is much to learn about not just the technology solutions, but also the economic and land use implications of these solutions. So we are looking to put out a request for information to get community input regarding technical white space and economic and environmental constraints. And so this will be coming out soon. So stay tuned and look for these opportunities, coming from ARPA-E. Another thing I want to highlight, because there is an opportunity, for folks to still apply. We have an open funding opportunity that we're soliciting proposals. You've seen what our interest is in ensuring that we can service a very large negative emissions industry with technologies that are low cost and energy efficient. If you have ideas that could achieve those aims that we're interested in, this open funding opportunity is going to be over $100 million of funding, and you could put in applications to ARPA-E to do that. So let me recap. The real thing to talk about here, and I teed this up in the beginning, is the bioeconomy is the way that we can really allow ourselves to maintain our economic prosperity in a carbon-based economy in a sustainable way, through using sustainable biomass as the feedstock for the various carbon-based products that we need. But in order to achieve the greatest sustainability, we need to be able to connect not just the bioeconomy, but other aspects of that supply chain to carbon markets to drive the right types of innovations to align with a robust carbon or climate strategy that we have for keeping global temperatures below 2 degrees. And so there's the need for carbon accounting because of the difficulties and the dynamics and the variability in ag systems. We really need new systems to ensure that we can get the most robust measurements of a carbon harvest. And what that will allow us to do is to allow the bioeconomy to provide us with negative carbon products, and it will facilitate our ability to realize a carbon farming industry in the future, whether that is through, the parallel pathways for traditional crops and feedstock crops, or through exclusive new types of farming systems that provide ecosystem services as well as carbon management and all of the associated technologies that would come with that. So that could be a very exciting program that we are, like I said earlier, we're going to be issuing a request for information and workshopping this idea in preparation of thinking about potentially developing and pitching a program in this space. So with that, I wanted to thank everybody and offer, my email. I'm a federal employee. I'm a public servant. You can email me. I always love to talk about these technologies. These are the ones that are focused in my ag portfolio, but I also, have a biotech program that I love to talk about. So I'm happy to talk to anybody, and I really appreciate the opportunity to speak to everybody.